All right, in this video we are going to finish up our transformations, and we're going to talk about the b value. Okay, meaning like this number right here. So let's say I have a graph of a function. Let's say I have a graph of a parent function f of x. How does changing the b value affect the graph? In my previous video I talked about a, h, and k, and so I want to start just by recapping those real quick. And so first off, let's talk about that a value. Okay. So if the a value was greater than 1, it would create a vertical stretch. In other words, if you had an original parabola that looked like this, and then you changed the a value to like a 4, it would create a vertical stretch. Okay? And then over here we said, what if a was a fraction? So if you had a parabola that looked like this, or really any function, actually let's do something other than a parabola. Let's say you've got a cubic function that looks like this, but then you change the a value to a fraction, like 1/2, it's going to create a vertical compression, which is going to look like you squeezed it from the top and the bottom. And then lastly, if a is negative, what that's going to create is a vertical reflection. Okay? And those are rough looking pictures, but you get the idea. And then we kind of shifted over here and we started talking about our h and k value. And so what that h value does is it controls our horizontal shift, okay? And we gotta be a little bit careful with this because it's the opposite of what you'd think. So let's say you had the quad, once again I want to get away from the quadratic, let's do the square root function, okay? But if you were to take it and you were to do like an x minus 2 to create this function, what that means is you just shifted it to the right 2 units, okay? If you were to take your function and say x plus 3, so instead of the square root function, you are now doing the square root of x plus 3, that would mean you took it to the left 3 units. Okay? And lastly, let's talk about this k value. I think the k value is a little more straight. Because if I had some function, I can even keep my square root function from the last problem, but if we were to take our function and add 5 to it in order to get the function square root of x and then a plus 5 that's over here not in the parentheses, okay, that means we're going up 5 units. And likewise, if you were to take your function and you were to have kind of like a minus 9 out to the side, not in parentheses, that means you're shifting down 9 units. And that was what we talked about in our last video. We kind of talked about these things. We haven't talked about the b value, which I think can be a little bit tricky. So let's jump into that for this one. So we're going to start with the quadratic again. I guess I'll do more examples with the quadratic parent function, because why not? And so just to kind of get our points, any value squared is going to be a positive. So negative 2 squared is 4, negative 1 squared is 1, so on and so forth. And let's start by graphing these 5 ordered pairs. And if I graph these, it's going to give us our quadratic parent, and that's going to be like our baseline by which we can compare how these are going to look after the transformation. Now, let's see what happens here. Oh, I'm graphing the cubic function. Let me back up and do that. It looks like I got a little typo on my slide. I like the idea of using the cubic function because it's different. So let me just change that to a 3 because it looks like I got it as a 3 there. So negative 2 to the third power is negative 8. Negative 1 to the third power is negative 1. 0, positive 1, positive 8. So let's plot these points. Negative 2, negative 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 1, 0, 0, 1, 1, and 2, 8. So here is what our cubic parent function looks like. I guess I am glad that I put something other than a quadratic on this slide. Now we're ready to play this game. Now what I'm going to do is I'm going to take the x value and I'm going to multiply it by 2 before I cube it. And let's see what happens. Okay? And so if I take the x value and multiply it by 2, I would get a negative 4. And negative 4 cubed, ooh, that's a big number. I'm thinking that's negative 64. And then let's do the same thing with negative 1. If I multiply negative 1 times 2, I'd get negative 2. And negative 2 cubed is negative 8. We have 0, positive 8, positive 64. So let's kind of see what happens here. It looked like when x was negative 2, y was negative 64. It's way off the graph, okay? And then when x is negative 1, y is negative 8. and then we have this, and then we have this, and then for positive 2 we're way off the graph again. So it really became this. Okay? And here's what I want you to think of it as. I want you to think of it as this point got squeezed, got compressed from the left to become this point. Okay? Because previously, when negative 2 would yield an output of negative 8, now a negative 1 is yielding an output of negative 8. Think of it as a horizontal compression. Okay? This has created a horizontal compression. Okay? And in order to see the idea a little bit better, I'm not going to mess with the negative for this video. I think we'd be better suited by doing like a 1/2 x cubed. Okay? So if I took negative 2, multiplied it by 1/2, that would be negative 1, and negative 1 cubed is negative 1. And then if I did negative 1, multiplied it by 1/2, negative 1 times 1/2 is negative 1/2. Negative 1/2 to the third is, that's going to be negative 1/8. And then we're going to have 0, 1/8, and 1. And let's see what this looks like. So when x is negative 2, y is negative 1. So when x is negative 2, y is negative 1. So we have that point now. When x is negative 1, y is negative 1/8. And then we have 0, 1/1/8, and 2, 1. So now our graph looks like this. Okay? And it would kind of keep going like this. And so what this is this is a horizontal stretch. Okay? I want you thinking of the fraction inside the parentheses as taking these points and pulling them outwards, kind of away from where that parent function started. Okay? This is kind of hard to remember because it's backwards from our vertical shift that we learned about in the previous one. Now if a is a fraction, that's going to stretch it horizontally. If a is greater than 1, that's going to compress it horizontally. So let's summarize real quick. I think I've got a summary on the next slide. Okay, so if we have a b value that is greater than 1, what that's going to create is that's going to create a horizontal compression. It's going to look like a squeeze. Okay, if if we have that fraction, that's going to create our horizontal stretch. It's like we're pulling it from the sides and making it wider. And what I didn't really address in this video is that if we have that negative, it's going to do a horizontal reflection. Okay? We're going to cut that out for the sake of time, but you could substitute in some, try it out with a b value that's negative and see that that works as well. So these would be the 3 categories I would want you to know. Once again, these transformations apply no matter what our parent function is. We just did it for cubics. It would also apply to quadratics, absolute value functions, cubics, whatever you want.